like to quick talk about a concept called chemical equivalence. And what we have here is a drawing where we see, if we look at this, we've got two hydrogens right there, which can actually be considered equivalent. They are not different. How about that one right there? That's those three hydrogens on that methyl. They aren't different. Even these three methyls here, they all are the same. Therefore, but notice too, this methyl here is not the same as these three methyls over here. Yes, they are both all three methyls, but they are different types of methyls. So what you end up with is three different signals. Signal 1, signal 2, and signal 3. Even though we have 14 different protons, they fall within three classes which are chemically equivalent. So we have a definition of chemical equivalence. And what we say is that protons which see the same chemical environment are shielded or deshielded the same, and therefore these protons will show up at the same chemical shift. The peaks will then represent, the peaks that are from the NMR will represent 2, 3, 4, 5, 6, whatever equivalent protons. So if we take a molecule, let's say that looks like this, the three hydrogens on each of these methyls are all the same, and therefore they'll show up at the same chemical shift. Let's just say 1.0, for example. And the hydrogens that are here, there's one there and one here, those will be identical, and you'll see the chemical shift there, let's say 1.6. And what you have to keep in mind is, well, how many hydrogens is represented by that signal? Well, we've got 3 here, 3 here, 3 here, 3 here, and 3 here. So we are dealing with 12 hydrogens at the 1.0 ppm peak. We are dealing with 2 hydrogens at the 1.6 ppm peak. And NMR is quantitative, so we can see this by integration, which we'll talk about next. In this session, what we'll do is we'll pick up finishing our talk about chemical shift, shielding and deshielding. Then we'll start moving into concepts of chemical equivalence and integration, and even start talking about splitting. So what I'd like to do here is talk a little bit about the chemical shifts of things such as methane or substituted methanes. So not the best drawing here. I probably should redo this one. So apparently I can't erase this guy. But what I would like to point out here is that the hydrogen should be on the carbon, not on the other hydrogen. So, but if we take, let's say, something like methane, we're talking somewhere around 0.9 ppm for those hydrogens. If we put a fluorine on it, that shifts all the way down to about 4 to 5 ppm. Significant movement, and that's because the fluorine is so electron withdrawing. The iodine is kind of in between, and that shows up in the chemical shift. It's about 2.7. So the types of groups that are attached to your hydrogens or adjacent to your hydrogens have a big effect. And that effect can vary from its distance from an electron withdrawal. So if we look at this molecule here, if we looked at the chemical shifts of the various hydrogens, we'd see that the hydrogen here is 4.5. The hydrogen on the methyl out here is 0.9. Here, 1.2 for those two hydrogens, 1.8 for these two hydrogens, and then 1.2 for that methyl over there. What you should notice is that the proximity to that electron withdrawing group up here, the closer you get, the more deshielded your protons are. And so that carries through for most molecules. So the further away you are, you see almost no effect out at that methyl group. But this methyl group is much closer, so it is more deshielded, and therefore requires a more downfield signal. So if we take a look at this spectrum, what we see here is 3 methyls that are all identical. All right, and we see this one methyl over here which has 3 hydrogens, and every single one of these hydrogens is identical. So we're really talking about a ratio of 3 to 9 for the 2 different signals. Now what integration does is exactly as we might know from math. Integration allows you to calculate the area under a peak. And so if we do the integration of the peak at 3 and at 1, what you'll see is this is the height. The height is going to be representative of the area. And the relationship or the ratio of these two is a 9:3 ratio. And so we can determine that the peak at 1 has 9 protons, the peak at 3 has 3 protons. All right? Here we have another example. If we look at the molecule that we're dealing with here, we have a methyl over here connected to the ketone, and then 2 other methyls over here. Notice methyl A and methyl A are again in the same chemical environment. They're bonded to a carbon, which is bonded to an oxygen, another CH2. So that is one signal right here. The methyl that's next to the ketone is a different methyl altogether, so that's a second signal. A third signal is the CH2 that's in between. And the fourth signal is this OH. So we have 1, 2, 3, 4 signals, but each of them are going to represent a different number of hydrogens. The signal in black is going to represent the peak that is the most upfield or the most shielded, and we see that here. All right. The methyl that's next to the ketone is going to be worth 3 protons, and we see it right here. Now the CH2 that we see right here actually measures out to be 2 protons, and then this one right down here is 1 proton. But notice the ratio. It's 0.5 to 1 to 1.5 to 3. That's just a product of ratios. It's not the actual number of the proton. It's just that's the lowest number. So you can't have 0.5 protons. So to have 1, you multiply by 2. Well, then you take 1 and multiply it by 2. 1.5 and multiply it by 2. 3 and multiply it by 2. And that's what gets us to our 6 to 3 to 2 to 1 ratio. We're going to move on now to a concept called splitting. And splitting is an incredibly important aspect of NMR, which gives us significantly more information than just the chemical shift alone. And the splitting itself is a concept where the protons that are on a molecule will actually interact with each other. All right, so let's say we have 2 hydrogens on this methyl right here. We say that this is a little magnet here, and this is a little magnet here, and it has its own magnetic field, and this one has its own magnetic field. Well, it turns out that if there is enough proximity between these two, they will actually talk to each other, and they can interact and affect the magnetic field of the other. So let's just really briefly talk about that. And so let's take a look at this example right here. HB, as listed, is equivalent. So these two are exactly the same. They're both going to be in resonance at the same time. But notice they have a neighbor over here. HA is their neighbor. Remember we just talked about when HB is in resonance and when these 2 protons are excited, they will have a neighbor which is not excited. And therefore, HB will have 2 peaks because it has 1 neighbor. And so we see a doublet. The peak is split into 2. So this is referred to as a doublet. Now, the other peak has 2 neighbors. And so that gets a little more complicated. And it turns out that it ends up becoming a triplet. And so we have a rule that we can talk about. So we have a drawing here of, let's say, a hydrogen. And the one, let's say, we're most interested in is this guy right here. It's aligned with its magnetic field. If we put it and pulse it with a radio frequency, what that happens is the spin will flip, and we get that hydrogen opposite the magnetic field. We go from the alpha to the beta state. Now remember, that proton requires a certain frequency. The other one may not. And so this doesn't necessarily go into resonance. And so what happens is that hydrogen can either have its spin pointing up, as it is in this one, or pointing down. And they are close enough to each other that they're going to interact. And so this magnetic field will actually reduce the vector because they're in opposite directions, whereas this one will increase it. And so what you end up having is one signal, all right, will then get split into two peaks because you actually have 2 possible states. The neighboring protons will alter the magnetic field one way or the other. So here, if you have 1 neighbor, you'll split it into 2 peaks. And we generate a rule, and the rule is called the n+1 rule. And what it states is that a proton signal is split by n equivalent protons to give n+1 peaks. So if we have a molecule like this methyl is adjacent to a CH2 with 2 hydrogens. So the n+1 rule will state that we are going to have 2 plus 1 peaks, or 3 peaks associated with the methyl. Now if we then take the opposite and say, well, what about this CH2 right here? Well, how many adjacent protons are there to that CH2? Well, we have 3 from this methyl and 3 from this methyl, so we'll actually have 6. So n+1 is going to actually be 6 plus 1, or 7. So there will be 7 peaks associated with just that one signal right there. Things get a little bit complicated. And so this gives you kind of an idea of what's happening with the splitting. The two hydrogens here can either have the adjacent be pointing up or pointing down when the two are basically in resonance or having their spins flipped. And so you can have one peak and here the other peak, so that's where you get the doublet from. If we have, let's say, one hydrogen here, let's say we're going to look at HA instead, it has two neighbors. Those two neighbors could be both pointing down, they could be both pointing up, or one could be up and one could be down. And it turns out that the possibility is actually greater for the one to be up and one to be down because, you know, one of them could be up, one of them could be down, the other could be down, the other one could be up. So you can have two possibilities. And that's why you get a triplet, 3 peaks, and the middle one is the largest. All right, so that's why we see a triplet. And it still fits with our n+1 rule. All right, and then if we move this guy up here, what you see is, again, the number of equivalent protons, protons will give you splitting. So if you have 6 equivalent protons, you get 7. And you don't have to worry too much about this ratio, but what you need to know is that they're always symmetric. So if let's say you have a quartet, you'll have a symmetric quartet. Same thing for 5. You'll have symmetry because they're based on the probabilities of your things being pointing up, pointing down. Again, not too critical to know, but the symmetry is definitely there. So we'll finish with that. And one last thing we have to say is that this splitting has a particular size to it. So depending on the nature of the molecule, you can actually have different distances between them. We will actually cover this in the next lecture session. I don't want to get into this now, but we'll bring this back up and talk about coupling constants in the next session.